This is problem number 7 from chapter 11. This is another goodness of fit test, slightly different from the one we've seen before, because in the one that we've seen before we saw that the expected frequencies were all the same. Here we have expected percentage of majors, or proportion, or probability, and they're all different. So when we make our list of observed values, observed frequencies, we'll see that, and expected frequencies, we'll see that our expected frequencies are all going to be different. And so in this particular problem they're not asking us to list it, but it would be good to know, and we won't necessarily list it here, but we'll have it in our calculators. Our observed frequencies are given in this column, and for us to be able to compute our expected frequencies, we need to figure out what the total is for our data set. So what you can do is you can type all this stuff in your calculator and add them all up, or better yet, if you have it on the list, I have mine in L1 already, 670, 410, 685. What we can do is, if we go back to the home screen, what we can do is add them all up. So I'm going to press second function in list and go to math, and the fifth one down is sum. So the sum of my list in L1 is 5,000. So I know I have 5,000 people that we counted here. Now to compute our expected frequency, what we're going to do is, for example, this Arts and Humanities section, it's going to be 14% of 5,000. And for biology, it's going to be 8.4%, and so the percentage, remember, needs to work as a decimal when you're doing math with it. So that's 0.084 times 5,000. As you can see, this can get a little bit tedious. So what you can do is go back to the list. Now, I already did this ahead of time, but in L3, what I did was I listed down the percentages as decimals. So the third one down is 13.1%, 13%. 2.6 is 0.026, and I just want to scroll down here to the technical. 0.04% is equivalent to 0.004 as a decimal, so be careful with small percentages like that. So anyways, I saved my space in L2 because this is where I want my expected frequencies to go. And what I'm going to do is, as you can see, my cursor is up on L2, so I have L2 down here with no parentheses. And what I'm going to do is I'm going to create a list, and my list is going to be this product of the percentages. I'm going to call it proportion times 5,000. Now I have my proportion in L3, so I'm going to, on my calculator, I'm going to type second function in L3 times 5,000. And then when you hit enter, this list will get populated with our expected values. So just to write down a few of them, I would expect, out of these 5,000 students, I would expect 700 Arts and Humanities majors, 420 biological science majors, 655 business majors, 650 education majors, etc. So that's how we can get our expected frequencies, where the distribution is not uniform. Now let's go ahead and proceed to the hypothesis test. So given our that this is a hypothesis test, we need the null and alternative hypothesis statements. So mathematically, our null is saying that 14% of women are expected to be arts and humanities majors, 8.4% biology, 13.1% business. So what we can do is, well, this is not preferred, but you can write down the probability for the first major is 14%. The probability for the second major is 8.4. Whoops, 0.084% or 0.084. That's the proportion. The percentage is 8.4%. Now this gets a little tedious. So what we can say is that the number of women majors, or number of actual majors, fit the expected frequencies, expected majors. Well, we should probably say the distribution of expected majors. And then you can just say the data doesn't fit for the alternative hypothesis. So here are our two statements, the null and alternative hypotheses. So now we need to figure out our test statistic, which is going to be a chi-square test statistic. And then we also need to figure out a p-value. And our p-value, we're going to be using our distribution, our skewed to the right chi-square distribution. So whatever our test statistic is, our p-value would give us the area in that shaded region. Speaking of, our test statistic, our distribution is going to be a chi-squared sub the degrees of freedom. Remember that the degrees of freedom goes here, and it's counting the categories minus 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 categories. Your DF then is going to be 10. Alright, let's do this computation. If you remember the test statistic, it's the sum of observed frequencies minus expected frequencies, quantity squared, divided by the expected frequencies, all over the number of categories we have. So here's our observed frequencies. Alright, it's in L1. Our expected frequencies are in L2. So it's L1 and L2, and this is L2. Let's go back to our home screen, second function, and quit. And let's call on our sum function again. So remember that second function, stat, math, and the fifth one is the sum. We're going to start off with an open parentheses. The observed values are in L1. That's second function, and the number 1, minus our expected frequencies, which is in L2, close the parentheses and square it, and then divide by the expected frequencies, which again are in L2. So here our chi-squared test statistic is 11.4835. So given our distribution and our value of 11.4835, what is our p-value going to be? So with our calculator, we go under distributions, second function, distributions. The chi-squared PDF is down here, but we want the CDF, so that's number 8 in my calculator. And remember, the chi-square CDF takes in a low value, and the region is shaded going upward here, so the low value is 11.4835. Our high value is infinity. Let's just call that 1 e to the 99. And it takes a third argument, which is our degrees of freedom, which we found to be 10. And so that's going to give us a p-value of 0.3211. So that's a pretty large p-value. So a large p-value means we failed to reject. So since the PV is large, definitely bigger than 0.05, we're going to fail to reject the null hypothesis. So remember that the null hypothesis is the actual majors fit the distribution, and so since we did not reject that, our conclusion would mean that the data supports, let's just say shows, that the distribution is a good fit. And then we can be done. Like I did before, I'm going to show you for the more advanced calculators, there's an actual GOF test, goodness of fit test, that's built in. So let's go to stat, test, and I'm going to hit the up button to find it a little bit quicker. So that's chi-square GOF. We have our observed and expected frequencies in L1 and L2. Our degrees of freedom in this case is 10. And we can calculate it, or we can just draw it out. The drawing, remember, gives you your test statistic and your p-value. Degrees of freedom is 10, will give us a nice skew to the right curve, and it'll actually shade in our value. So our chi-squared is 11.4835, and our p-value is 0.3211. And this is how the drawing would look like. Alright, so hope that helps with your homework.